Okay, last part of this video, let's do another example. Let's say f of x is equals to 2x plus 1 divided by x minus 1. Again, first step, switch x and y and solve for y. And then we switch it, multiply the denominator up, and then expand it, and then get y on one side and all the x's on the other. So when you y, factor the y out and get by itself, so you have y times x minus 2 equals x plus 1. And then you get y by itself, y is equal to x plus 1, x minus 1 minus 2. That's my inverse, my f of x. Okay, a word of caution though, if you have negative values, you want to try to move it to the other side where you make it positive. In that case, you won't have to worry about positive and negatives. Okay, so in personal experience, if you have positive and negative issues, then that's usually where your algebra happens and that's where your mistakes come from. Okay, let's talk about the domain and range here. So my f, this is my function f. Okay, so again, denominator cannot equal 0, so x cannot equal 1. So in that case, my domain here is all real numbers except x equals 1. Okay, that implies my range here is all real numbers where y cannot equal 1. Okay, just remember switch your x and y. Now, for my domain of this one, it's going to be all real numbers except x is equal to 2. That implies my range for my original function is all real number except y is equal to 2. Okay? So let's go ahead and verify our determine my f and inverse of f are indeed inverse of each other. So in this case 2, my outside function is my f, so I use this and replace my x's in here with the inverse. In that case my inverse here is x plus 1 divided by x minus 2, and then x plus 1 divided by x minus 2. Okay? And then again, adding fractions, get the same denominator, multiply everything out and simplify. This gives us this, and then you end up with 3x over 3, which simplifies as just x by itself. Okay, next part. Inverse of f of x. Inverse of f is on the outside, so use this to replace all my x's with 2x plus 1 and x minus 1. In that case, we have 2x plus 1, x minus 1, 2x plus 1, x minus 1. And then same procedure here, simplify, and you get 3x over 3. And then that simplifies as x. And yes, since these are both equal to x, we have verified that they are indeed inverse of each other. Okay? A word of caution, always pay attention to your algebra. That's where most of your mistakes will come from. Okay? Now, next thing, then the part where we talk about, remember the x squared idea and how it doesn't pass the horizontal line test. But if we restrict the domain, in this case, restrict it as values greater than 0 or less than 0, something of that nature, you can go ahead and use you can find the inverse by restricting the domain. So let's go ahead and do the example. F of x is equal to x squared. Again, let's find the inverse. Switch it and get x by itself. Okay, so usually what would happen here is when you take the square root of a number, you end up with square root, you'll have the plus and minus. But in this case, we won't have to look at the minus. In a little bit, I'll show you why. Okay, so in that case, doing all this, and you end up with y is equal to square root of x. Okay, since y is by itself, that means inverse of f is equal to square root of x. Okay, so let's talk about this. Because we're restricting the domain where x has to be greater than 0, so all the numbers, no matter what number you put in here, as long as it's greater than 0, it will pass. So in that case, anything greater than 0 you put in here, f of x must always be greater than 0 as well. Okay? Okay, so that's what we have. So that means that's why we have, this is strictly positive because of the number you can only put into x. X can only be greater than 0. And that means the square root of a number can always only be greater than 0. Okay? So that means my domain here is x has to be greater than 0. Okay? That means my domain and my range here, sorry, let me write that. My domain and range. Okay, so that means my range here, because of my domain for this function, we have y has to be greater than 0. Okay? Now let's look at the domain of this one. X cannot be a negative number, but it can be greater than 0. That means my domain here is x has to be greater than 0. That means my y has to be greater than 0. Greater or equal to 0. And that's what we have. Okay? So let's go ahead and verify our answers. So f is on the outside, so the x squared, and then replace the x with square root of x. So square root of x squared comes out as x. Okay? And then inverse of f, inverse of f is the square root, and then replace the x with x squared. Okay, x squared, the square root of x squared is just going to be x by itself. Okay. Now so if you graph this diagram, you end up with something like this is the part where y is equal to x squared, where x is greater than 0, greater or equal to 0. And then because remember, we talked about the idea that it has to be reflected across y equals x. Okay, this is a rough sketch, bear with me. That means my inverse function here is going to look something like that. So in that case, it's going to be y is equal to square root of x. That's my inverse function, and then because of restriction there, we have our function. Okay, so what happens here, because we restricted the domain where x has to be greater than 0, that's why my square root of x, my x squared is only on the positive side. Okay, and in that case, we have successfully inverted y equals x squared by restricting the domain. Okay, so for next lesson that's coming up Monday, if we have class or not, physical contact or not, in that case, what we end up with is going to talk about the inverse trig function. So inverse of sine, inverse of cosine, inverse of tan, inverse of cosecant, inverse of secant, and cotangent, inverse of cotangent. Again, word of reminder, caution, the -1 in this situation, those are not powers. Okay, that's not the same thing as 1 over sine of x. Okay, 1 over sine of x is cosecant of x. So don't make that mistake. Okay, so now I want you to go ahead and work on the handout and turn in by 9 p.m. Thank you.